that C is 30 microfarads. Okay. We go to the next part. It says, what is the charge stored on each charge? Nice. Charge stored on each capacitance. So we know that this is 30 microfarads. It's 30 volts. Then we know that C is Q over V, or Q is CV. So in this case, Q is 900 microcoulombs of charge. So 900 microcoulombs of charge. And then that charge just gets distributed through the whole thing. So this is going to be plus 900, there's going to be minus 900, that's plus, that side would be minus, and of course, now we have to say through here what happens. Well, it's going to get split evenly through all of these. So this is going to become like plus 300, plus 300, plus 300, minus 300, minus 300, minus 300. Because remember, there's no difference between each one of these capacitors individually or just adding them all up, because they're all in parallel. Okay. Now E. And 2C says if you place the bulb just to the right of the battery, describe what happens from the moment you turn the circuit on until a long time. So let's look. And then say, okay, so we know that the current versus time is going to go like this. Right? There's going to be a big current in the beginning because it's coming out, it's filling in all the batteries, and then as time goes on, the battery is filling all the capacitors. As time goes on, the current diminishes. So we can say, therefore, the bulb lights, then dims slowly. Yeah, okay, there you go. Dims, and then the bulb goes out. So once the capacitors are full, the bulb goes out. Good night. If you want to create a bulb that has brightnesses, okay, so here we go. We have this. Alright, how this thing works is there's going to be R1 here, there's going to be R2 here, and then we're going to have, so we have three resistances, R1, we have R2, and we have R1 plus R2. Alright, and now we know that the electric potential across everything is constant. It's 110 volts. So what we're going to do is I'm going to say what P involves V and R. So I'm going to say P is V squared over R. Yeah, okay, so then we can say, from one aspect, we don't know what R1, now if we think about this logically, when is it brightest? Well, what does resistance do to the brightness? The bigger the resistance, the lower the power, less the brightness. So the bigger the R, the lower the P, so the lower the brightness. Okay, so we know that the 50 watt, the 50 come from here. The lowest power is going to come when both resistances are there. And let's just, for grins, say that R1, that R2 is bigger than R1. So we'll say this is the 100 watt, this is 150 watt. So now we can say, we can just write three things. 150 watts equals 110 squared over R1. And we can say 100 watts equals 110 squared over R2. Or actually, the way I would want to do this is I'd want to say R is equal to V squared over P, and then just solve it. Okay, and there you go. So R1 is equal to, what is this is 11 times 10, so it's 121 times 100, 1.21 times 10 to the fourth or something, divided by 150, and then R2 is equal to 1.21 times 10 to the fourth, divided by 100, so that knocks off that. We get 121 ohms. This one I'd have to call in a calculator. Okay. Of course, I don't have a calculator in hand, so I'll have to use my iPhone here. 1.21 times 10 to the fourth divided by 50 gives me 80.7 ohms, and that makes sense because we said that the second one's going to be bigger than the third one, and of course the total, you just add them together, and there you go. Done.